Hey guys, we've been talking a little bit about vectors with the electric field, and I figured it'd be a good thing to get you guys a video uh, to give you a little bit more information about vectors. We've talked about them uh, quite a while, so it's good if we just go over them. So, what is a vector? So we have things called vectors, we have things called scalars. Okay, vectors have magnitude and direction, whereas scalars just have direction. So it's just the quantity that you're calculating. So just like 5 meters, oh, I'm sorry, just magnitude. Magnitude. So just like 5 meters, 5 newtons, 6 kilometers, stuff like that. Whereas over here, you'll have 5 meters north, 6 meters in the x direction, or 3 meters towards, I don't know, Galway. So all these are examples of vectors, and all these are examples of scalars. Just the magnitude on scalars. You want to remember with vectors, think V as an arrow, and there you have a direction for your vector. So let's do a little bit of an example problem, two different ways, okay? So if we have an axis here, we say this is x, this is y, this is negative y, this is negative x, or sorry, negative x, negative y. This could easily be north, south, west, and east. All of this stuff is arbitrary. It's what you, the person who's building this graph and the information you want, or whoever you're giving the graph to, the information that they need, that's how you're doing it. There's nothing special about X or Y. You could call it F or smiley face and baseball hat. It doesn't matter. As long as you denote them differently, okay? So if we look at a vector, if we say that we have this vector, okay, and this vector is in this direction, and it has a magnitude, so the vector has a magnitude, its length, let's say, is 10, okay? It's 10 meters. Let's say we're doing direction, or distance rather. So it's 10 meters, okay? 10 meters. And we're also going to say that this is at 45 degrees off of the x-axis. So whenever we say 45 degrees off of something, we say it's 45 degrees, or we mean that it's starting from x and it's going off of x like this. If it was, in fact, 120 degrees off the x-axis, and we'd go all the way around, so that's 90, yeah, and then 30 more degrees to about here. So this would be 120 degrees off of the x-axis. Right now we're only interested in 45 degrees, okay? So 45 degrees off of x-axis. Now, we've said that when we're drawing vectors, we might want to put an arrow over it. You might have heard this in maths, or you might have heard this in physics. Now the arrow may look different. It may just be a line with kind of like a dash. Actually, that looks pretty bad. So it could be like that. It could be like this. It could be a few other different ways, but those are probably the ways you see it. That just means vector. So whenever you see that from now until whenever is it just means a vector. It's the way of writing it. Okay. So in this case, A, I could say, is 10 meters northwest. Okay. So if I look at this, I pretend this is north and this is west and east. Actually, sorry, be northeast, wouldn't it? Northeast. Okay, in the northeast direction. But I've already denoted this x and y. So what I have to do is I have to figure out how much in x and how much in y this vector is. So what I do is I use trig. And so we have sine, opposite over hypotenuse. We have cosine, sorry, this is theta, cosine of theta, adjacent over hypotenuse. And tan of theta, which is opposite over adjacent. What you can prove on your own is that sine theta over cosine of theta also equals opposite over adjacent. Okay? So, how do we figure out how much in the x that you've gone with this 10 meters and how much in the y have you gone or traveled as well? So, what we do is we break this guy up into its components. And what I usually do is break it up like this. And so my vector A, remember vector here, has an x component in the x direction and a y component of magnitude, in the y direction. Now it sounds a little redundant, but and you don't have to write these like little hats here or anything like that. It's just something that I've gotten used to over the years. But just know whenever I write this, I mean in the x direction and in the y direction. So let's calculate it. So a of x, because x, or actually we can do something before that, may make it a little bit easier, is what we're going to do is we're going to take this and draw it kind of like a triangle, or exactly like a triangle. So if you join this down here, and you can see that this is a triangle right here. Well, we know this is where the trig comes in, because we know the rules that describe this triangle. The rules are right here. The sine, this cosine, and this tangent. So the longest part, the hypotenuse, are 10 meters. Whereas this is the x component, and this is the y component. And this is 45. So we know that cosine of 45 deals with the adjacent side. So the ax is the adjacent side. Ax over the hypotenuse, which is 10. We know that sine deals with the opposite side, ay. So all we have to do then is determine ax and ay. So what we do is we cross multiply. So we have cosine 45, ax over 10. We just multiply each side by 10, because we can do that. And then we get ax equals 10 cosine 45. We do the same for the other one, and we also get 10 sine, or we get 10 sine of 45. Now, 45 degrees is a special one, in that cosine of 45 is the exact same as sine of 45. And what that equals is square root of 2 over 2. So if I have my original vector A that I drew up there, it has, remember, an x component in the x direction and a y component in the y direction. This is my magnitude. This is my magnitude. And this is my direction 1. This is my direction 2. And if I have magnitude and I have direction, then that means I have a vector. Okay? So ax equals 10 square root of 2 over 2 in the x direction. Remember, I didn't use my units. I should always use my units. This is meters. Meters, like that. Plus 10 square root of 2 over 2 in the y direction. And so that equals my vector A. But what if I wasn't given A? What if I just said that there was some guy, some dude, and I told that dude to walk in the y direction for 10 times square root of 2 over 2 meters, and then I told him to turn right and walk in the x direction, that same distance, 10 square root of 2 over 2. We have no idea about this vector right here, okay? We have no idea what that is. But once he gets there, I want him to figure out what his magnitude is from the origin, and I want him to find out what his direction is, or his angle off of x. The way he would do that is the same way, well, kind of the same way, is he knows he's traveled this distance, and he knows he's traveled in the y direction 10 square root of 2 over 2, and in the x direction 10 square root of 2 over 2 as well. But he needs to calculate this third side. And that's where Pythagorean's theorem comes in. And that says that a squared plus b squared, where a could be one side, b could be the other, side that isn't the hypotenuse, so they're the ones that straddle the right angle, equals the third side squared. And so if we plug that in, again, we don't know what this is, even though we kind of were doing it backwards of the thing we did before. We're just kind of trying to prove what we already know. So we have 10 square root of 2 over 2. We square that. B is the same way, 10 square root of 2 over 2. That equals c squared. There. So 10 times 10 is 100. We can square each of them individually since they're multiplied together. Square root of 2 over 2 equals 2 over 4. Same thing over here. But 2 over 4 is just 1/2. 1/2 of 100 is 50. 50. 50 plus 50 equals 100. So that equals c squared. So c must equal 10. It could also equal minus 10. But we'll just take 10. So what we've done is we've actually proven backwards, kind of, what we know all the way up here. Okay, so that's just a rough idea of taking a vector that we know, breaking it down into its components, and then also, if we know its components, how to get back to that vector. It works for all angles, it works for all vectors. And so try this out. Try it with 45 degrees first, then try it with 30 degrees, and maybe 60 degrees. Then try it with 90 degrees and see what you see. Okay, you should notice something special about 90 degrees, 0 degrees, 360 degrees, and so forth, and so on.